Okay. And common base configuration. Okay. Let's say you are being given with C parameters. Okay. So with the C parameters, how will you find the CB parameters? How will you find CB parameters? So HIB is, again, if you look at, this particular equation, okay, HIB. So you have been given with C, right? So HIB is equal to the same equation if you see. HIE divided by 1 plus HFE. Okay, so I'm not explaining anything over here. I'm just trying to, help you to figure out the things. Okay, the similarities. Okay, it takes some time to memorize these equations. Okay, no worries. If you have any trouble in memorizing this equation, you can skip off and you can attempt the different question in external examination. If you can memorize, this is the trick what you can follow. Okay, all right, fine. So that's about your relation between H model of C, CC, and CB. Okay, so this it's rarely they last. Okay, less likely to. Less likely to come, however, which is required for lab. Lab, it is required. Okay, but in lab, what I will do, normally I'm a guy who doesn't promote students to buy at the things. So in lab, what I will do, even in externals, I will try to give you these conversion equations. Okay, all you need to do is the experimental setup is your headache. Okay, but you don't have to memorize the formula. I will provide you, okay, as a appendix. Okay, as an appendix, I can provide you in the lab. Fine. So that's about the first topic of the day, which is relation between H model of CE, CC, and CB. Okay. Next, let me take up Darlington circuit AC analysis. Okay. See, I had given you the AC equivalent circuit question in internals, right? You could do it because AC analysis doesn't differ much with the conventional single stage emitter follower circuit, right? The H model or RE model remains the same for Darlington emitter follower circuit or a conventional single transistor emitter follower circuit. Okay, no problem. I'll just quickly tell you how exactly you determine the performance parameters. Okay, so figure A represents the circuit diagram. Okay, as you can see, this is based on the basis of emitter bias circuit, right? You have resistor RB and you have biasing resistor RA. Okay, one noticeable difference is that it doesn't have a collector resistor. Okay, this is what is required for an emitter follower circuit. Okay, there are two transistors having individual gains as beta 1 and beta 2. So for our analysis, what we will do is we will consider these two transistors as a single transistor with an overall gain as beta D. Okay, and that overall gain beta D, we can define it as beta 1 into beta 2, which is approximately beta square, provided beta 1 and beta 2 are very close to each other or they are identical to each other. So the overall current gain is beta square. Okay, and the other important aspect of emitter follower circuit is that the output is absorbed from emitter terminal. Okay, so the output is not absorbed from collector terminal, like your unlike your amplifier circuit. All right, fine. So that's your circuit diagram, and figure B, talks about the equivalent circuit. Okay, since there are two transistors, beta 1 and beta 2. Okay, so each transistor will have beta RE or HIE, right? So what we have done over here is that since we are replacing the two transistors with a single transistor, hence we have taken the overall input impedance of the Darlington pair as RI. So RI is overall input impedance of Darlington pair. All right. So On the input side, we have represented Ri, which represents the overall input impedance of Darlington pair. And on the output side, this collector current IC flows, right? So this is your collector current IC. This is your base current IB. Okay. And this is your emitter current IE. Okay. So IC is given as beta times IB. Since we are talking about a Darlington transistor, it becomes beta D times IB. All right. So that's your IC. And on the emitter side, you have an ungrounded emitter resistor. I mean, not ungrounded, non-short circuited emitter resistor. That's the reason, RE exists. Okay, fine. And the capacitor, okay, C0, you're going to short circuit. Okay, and the output voltage is observed right across the emitter resistor. All right. And on the input side, you have conventional input current IA. Okay, and some current IX will flow through the biasing resistor, and the remaining current will flow in as the base current IB. All right, so this is your equivalent circuit of Darlington emitter follower. All right, fine. Now let us look at the performance parameters. First, let us find out Zi. Okay, pretty simple. Okay, just like your emitter follower, you can find out Zi as well. So what we will do is, let us define, an assisting impedance ZB. Okay, so ZB we have marked very close to the base terminal. Okay, and we will shift Vi, okay, on the base terminal. Okay, next to base terminal, let us shift the input voltage. Okay, so you can write the input voltage Vi as, you can apply KVL. So that's IB into Ri plus IE into RE. But IE is basically 1 plus beta D times IB, right? So beta D you need to bring in. Okay, it's not just beta, it is beta D, and therefore you would get Vi as IB times Ri plus IE. So I'm going to replace IE with this. That's 1 plus beta D into RE, right? So that's your Vi. Or you take out the ratio Vi by IB, voltage by current ratio is impedance. And that impedance ratio, you will get it as Ri plus 1 plus beta D times RE. Okay. So that's your ZB. Therefore, input impedance Zi is equal to the base resistance RB, which is nothing but the biasing resistor, in parallel with ZB, right? So that's your overall input impedance. Okay, and I can here itself propose the approximation. So ZB can be approximately written as Ri plus beta D times RE. Okay, approximately you can write it down, no problems. Okay, fine. And this beta D is very large. Okay, let me write it in words. Is very large, and if it is found that beta D into RE is very much greater than RE, your ZB going to be simply beta D times RE. Beta D times RE. Provided the product beta D into RE is very much greater than RE. Okay, so that's your input impedance. Okay, so next let me take up the current gain AI. Current gain, yeah. Okay. So current gain AI is equal to output current to the input current. Okay. Now, in order to find a current gain, okay, over here, the current gain analysis is not that straightforward. That's because there are two transistors involved. Okay, even though we have taken the overall current gain as beta D, okay, it makes sense to provide the realistic picture of current gain. Okay, that's the reason, you know, I'm following this type of derivation. All right. So what I will do, I naught by II, you know, let me write it in this manner. So I naught divided by, don't worry, what is it, into, don't worry, what is the numerator, write down II. Okay. And then what you do is multiply and divide by IB. Okay, so mathematically, no harm done, right? Because IB is gonna cancel out with this IB, so you are left with I naught by II. Now, by doing so, what we get is a proper relationship between the two currents. Okay, because on the input side, you have current II as well as you have current IB, and on the output side, you have current I naught. So you will be able to you know, relate all these currents together. Okay. Now we know that. Okay, but we know that I naught is equal to IE. Okay, let's say equation 2, and let's say this is equation 1. All right. So therefore, we can write current gain AI as I naught, which is IE by IB. All right, into IB by IA. Okay, and we shall take this as equation 3. Okay, also we know that IE is equal to 1 plus beta d times IB. Okay, or approximately you can write it as beta d times IB. Okay, so what we will do is or you know, that implies the current gain beta d is IE divided by IB, and we shall take this as equation 4. So IE by IB is beta d. So you can sub equation 4 in equation 3, so that you will get current gain AI as beta d into the input current ratio IB by IA. Okay, so let's take this as equation 5. Okay, now IB by II relation can be obtained from the input circuit. Okay, that's because both IB and II are found on the input circuit. All right. So what we will do is, let us apply KCL. Okay, let us apply KCL at let's say node B dash. Okay, B dash and B is one and the same. I don't want to erase B, so I'll just take B dash. So if I apply KCL at B dash, what do we get? Summation of incoming current is equal to outgoing current. So II is equal to IX plus IB. We shall write it. So at node B dash, apply KCL. So what do we get? We get II is equal to IX plus IB. Okay, or II is equal to IB plus IX. So IX is nothing but current through the biasing resistor RB. So what is IX? IX is nothing but voltage divided by resistance. So I can write IX as voltage divided by resistance, that is RB. Okay, fine. Okay, or okay, so yeah, then also from the circuit. Okay, also from the circuit, you know, you can write II as, if you see, okay, also you can write II is equal to the total voltage, okay, that is VI plus IB into RB, okay, IB into RB divided by the resistance RB. Okay, so from the circuit we have Vi is equal to IB into ZB, okay? Or you can write, okay? So substitute equation 6 in equation 5, okay? So IB by II ratio we know, so we can substitute equation 6 in equation 5. So that will give us current gain AI as beta D into this resistance ratio. Okay, that's RB divided by ZB plus RB. So that's a current gain. Okay, that's a current gain. Okay, so ideal current gain is beta D, but from your actual circuit, you would get the actual current gain as beta D into some limiting factor, and that limiting factor is nothing but RB divided by ZB plus RB. Okay, so that's your current gain. Third one, voltage gain. Voltage gain is also very simple. So to find voltage gain, what I will do is I will recreate the circuit. Okay, this is your base terminal. This is your RI, okay, and then you have your RE. Okay, so this is your ground terminal. Okay, let us mark VI here, minus plus. Okay, this is your RE. Okay, through RI, current IB flows, and through RE, current IE flows. So therefore, okay, and this itself is V naught basically. Okay, voltage which is appearing across RE is our V naught. Okay, let me show you in the main circuit. See, voltage across RE is V naught. So same thing I have shown in the equivalent circuit as well. Okay, so therefore you can write V naught is equal to current into resistance, that is IE into RE, or IE is 1 plus beta D times IB into RE. Okay, so let's say equation 1. Then on the input side, you can apply VI is equal to, okay, you can apply KVL. So what do you get? IB into RI, okay, plus IE into RE, which is equal to IB into RI plus IE, let's write it as 1 plus beta D times IB into RE. Or you can even use voltage gain expression, because you have V naught and you have VI. What is voltage gain? Voltage gain is ratio of output voltage to input voltage. So therefore AV is equal to V naught. So V naught is 1 plus beta D into IB into RE, okay, divided by VI, which is IB is common. All right, so let me take IB outside the bracket. So within the parenthesis, I'm left with RI plus 1 plus beta D times capital RE. Okay, so IB gets cancelled. So voltage gain, you will get it as RE divided by RI plus 1 plus beta D times RE. Okay, so this is the exact expression. Approximate expression, just to show that voltage gain is closer to unity for an emitter follower circuit. So approximation you can do. Okay, so numerator remains RE. Okay, in the denominator you can write RI plus 1 plus beta D, we shall take it as beta D, okay, into RE. All right. Okay, so yeah, here also, right? This is also beta D into RE. I'm so sorry. This is 1 plus beta D into RE. I think I missed out this term. Okay, so 1 plus beta d, we can write it as, approximately beta d. So you have beta d into R in the numerator. Similarly, in the denominator, you have beta d into R. Okay, or approximately, you can also take the denominator as beta d into RE, as beta d into RE is very much greater in comparison with RI. So basically, these two will get cancelled out with each other. Hence, you will get voltage gain approximately equal to 1. Okay, that means to say for a Darlington emitter follower circuit, output is equal to input and phase shift, okay, between V0 and Vi is equal to 0 degree. So it doesn't amplify the signal, and it doesn't even change the phase value of the signal. Okay, it simply transfers a signal from one port to the other without any amplification. Okay, fine. So that's your voltage gain. Okay, the third one is the output impedance. Output impedance. So this output impedance is pretty tricky. Okay. So for output impedance, let us do it on the basis of Thevenin's theorem. All right. So what I will do for the output impedance, you can apply Thevenin's theorem. Okay, that is short circuit Vi. That implies Vi is equal to 0. Okay, and you can actually open circuit the ideal current source. Okay, ideal current source. But what I will do, I will just stick on to the approach which is being used in Boylsted textbook, and in the later half I will propose my approach. All right. So what I will do, I will apply Thevenin's theorem. So on the input side, I'm going to create a short circuit. Okay, this is my ground, and this is where my Vi used to be. Okay, and then you will have your base terminal, across which you will find your base resistor RP. Okay, and then you will have your input resistance Ri. Okay, that is later gets connected to the emitter terminal, and between emitter and ground, you are going to have the current source. Okay, beta d into IB. Okay, and you will have RE. Okay, so what we will do is we will consider a pessimistic voltage source V across the output. So this is my pessimistic voltage source. Okay, which is meant for the calculation purpose, that's all. Okay, so let us assume that this pessimistic voltage source is circulating some current I. Okay, some current I. Now at this node, what happens is that this current is going to divide into two parts. Okay, let's say I dash through RE. Okay, sorry, this is your upward current direction, and beta d. Okay, now since this is short circuiting this particular resistor, what will happen is this will vanish. Okay, because this short circuit will remove the base resistor RB. Okay. So due to which what will happen is you will be left with Ri here. Okay. So I'm just shifting it here, and then the emitter terminal, Okay, and then this resistor. Okay. See, this emitter current we have simply replaced with beta D times IB. Strictly speaking, it should have been 1 plus beta D times IB, but for reference, we have taken it as beta D times IB. Okay, and this is your RE. Okay, and this is your voltage source V. Okay, which is connected just for the simplification purpose. Okay, so this is I, and this is I dash. Okay, and this current, this current we can take it as IB because that's the base current, right? So apply KCL at node E. Okay, node E will give us IB, incoming current, plus the second incoming current, beta D times IB. Okay, then you have, okay, this current, okay, this current, which is I minus I dash, correct? Because this current I enters at this node. Okay, I mean it meets at this node and it is going to divide into two components: I dash component through RE and some component through this straight path. Okay, and that current, you can find using KCL, which is main current minus the branch current. So I minus I dash. So here, let me directly write plus I minus I dash is equal to 0. Okay, but expression for IB is already known. Okay, expression for IB is basically V divided by RI. Okay, and there's a negative sign. Okay, because see, the voltage across beta D IB, okay, is 0, right? Voltage across ideal current source is 0. So whatever voltage that appears across RI is nothing but this voltage V. Okay, but remember that the current direction, through RI, we have taken it in clockwise direction, but your pessimistic voltage source V is trying to circulate the current in the opposite direction. Hence, the negative sign is being placed. Okay, and on the output side, you can write I dash is equal to V divided by RE, right? I dash is nothing but voltage across RE divided by the resistance. Okay, now here the current is actually matching. Okay, current is actually matching the source current sent by voltage source V. So you will find a positive sign over here. Okay, let's take this as 2. Let's take this as 1. So substitute 2 in 1. Okay, so when you substitute equation 2 in equation 1, you would get IB is equal to minus VI by RI plus, okay, what I will do, just minus I will write, because I will write beta D into IB. IB again minus V by RI, right? So minus V by RI. That's the reason there is negative sign here. Then plus I, okay, and then minus because there is minus sign, V by RE. Okay, or you can write I is equal to, okay, what you do is equal to 0. You take all voltage terms onto the right hand side. So you would get I is equal to V by RI plus beta D into V by RI plus V by RE, or you can take out the ratio, okay, V by I. Okay, before that, let me take out all voltage terms outside the bracket. So this is V1 divided by RI plus beta D divided by RI plus conductance, that is reciprocal of RE, or take out the ratio V by I. So voltage to current ratio, let's define it as output impedance Z0. So Z0 is basically reciprocal of all these. So that's 1 by Ri plus beta d Ri plus 1 by Re. Okay, so that's your Z. Okay. Or because you're taking out the ratio, or you can directly write Z0 as, okay, Z0, or Z0 can be represented with the help of 3 resistors connected in parallel. Okay, that is something like this. Ri, and this is your, again, reciprocal of this, right? So that is Ri by beta d, and the reciprocal of this, that is Re. So this is V, and this is I, and this is your Z0. So you can write Z0 as Ri parallel with Ri by beta d parallel with Re. Okay, so that's your Z. Okay. But remember one thing, this ratio Ri by beta d, okay, this is small and this is large. Okay, so due to this, small and large values, what happens is that ratio Ri by beta d is very small. So it's something like you are connecting a small resistance in parallel with the 2 other resistances, due to which your Z0 will be the least resistance among the lot, right? Amongst others. That's because Ri by beta d is very small. So your Z0 is approximately equal to Ri divided by beta d. Ri divided by beta d. Okay, so this is your output impedance. So this shows that output impedance is very small, very small. Okay, so that's your analysis. Zi, Z0 we have found, and then we also found EAV and EAI. Okay, so the important characteristics of Darlington emitter follower is that current gain is very high. Then voltage gain is unity with 0-degree phase shift. Okay, and high input impedance and low output impedance. The applications are something like impedance matching. Okay, just like your emitter follower, impedance matching. That's the first application. And the second application, it can be used as a buffer amplifier. Okay, buffer amplifier is nothing but isolating circuit, just like your transformer. Okay, and since beta d is very high, okay, it can be used as current amplifier. Current amplifier. If you want to increase the value of output current, Darlington emitter follower is the best circuit to use, simply because the overall current gain is theoretically the product of individual current gain.